Hello and welcome back to the alphabet of astronomy. Today is brought to you by the letter G, and G is for globular clusters. I don't know why I said it like that. That was weird. I'm sorry. I'm just in a weird mood today. Okay, we're gonna talk science. Sorry. Focus. Okay, so globular clusters. So this is a globular cluster. I think they're pretty cool looking, so we'll be showing some pictures of them because who doesn't like to look at cool astronomy pictures? But basically a globular cluster is just a spherical, tightly bound group of stars. This particular one is called M13. So globular clusters are typically found in the halo of a galaxy. And when we talk about the halo, we mean this kind of spherical region that's not really like the disk or the bulge where the kind of majority of the matter, or at least the majority of the stars are. The Milky Way has over 150 globular clusters that we know of, and probably less than 200, even including all the ones we haven't detected yet. Other galaxies have a lot more. Larger galaxies tend to have more globular clusters, and elliptical galaxies actually have a lot more globular clusters, as opposed to spiral galaxies like the Milky Way. So for example, M87, which is a large elliptical galaxy, has tens of thousands of globular clusters. So globular clusters are usually composed of what we call population 2 stars. So what are those? Well, population 2 stars are older metal-poor stars. Now, just as a note, when astronomers say metal, we mean anything heavier than helium, so don't just think the things you might traditionally think of as metals, but any heavy elements we would consider metals. So these are metal-poor stars that are primarily made up of hydrogen and helium. This is in contrast with what we would call population 1 stars, like our sun, which are younger stars that are more metal-enriched. And the reason that younger stars tend to have more metal in them is because these metals are created during the life cycle of stars. And so kind of earlier generations of stars are going to have less metals, and then they create more metals and they enrich the medium that future stars form from to have more metals in. And in fact, it's postulated that there exists what are called population 3 stars, which would have been the very first generation of stars that would have been almost completely made out of hydrogen and maybe a little helium. And these stars would have been very massive and died very quickly, providing just a few heavier elements to go into the population 2 stars. However, population 3 stars have never been directly observed, although astronomers are hoping that JWST, which is supposed to launch later this year, might help them detect the very first population 3 stars, which would be really exciting. Also, just a note, if you think about the order in age, population 3 is the oldest, and then population 2, and then population 1 is the youngest. That might seem kind of backwards. Welcome to astronomy. But just a note to keep in mind. So astronomers actually think that most stars are born in clusters because those are areas where the interstellar medium becomes dense enough to kind of start collapsing and forming these stars. So it's going to form quite a lot of stars right near each other. However, a lot of these clusters, as the gas is blown out by these massive stars and supernovae and other effects, they become unbound and they start to drift apart. So we think that our sun was probably born in a cluster that later dissipated, for example. These types of clusters are called open clusters, in that they are open, they are not bound, they are eventually going to dissipate. This is in contrast with globular clusters. So these are tightly bound, and they're bound together gravitationally, they are not going to dissipate. And globular clusters, like I said, they're made out of population 2 stars, which are old stars. So globular clusters are very old. So all of the gas and dust is gone, just as it would be in an open cluster, but the globular clusters remain bound anyway, due to their large number of stars. And the fact that they're gravitationally bound is what kind of gives them this characteristic globular or spherical shape. That's from gravity. In fact, some globular clusters are so old that we've even used them to help constrain the age of the universe. And it concurs with other evidence that indicates we live in a dark energy universe, but that's not what this video is about, so just an FYI. So in order to be tightly bound like this, these globular clusters are very densely filled with stars. They contain tens of thousands of stars, and the diameter is up to about 100 parsecs or even less. This means that on the outskirts of a globular cluster, the stars are probably on average maybe about 1 light year apart, but at the center of a globular cluster, they're only hundreds of AU apart. While this isn't exactly dense in the sense that they're banging into one another, it's very dense in an astronomical sense. If you think about the sun, our nearest neighbor star, Proxima Centauri, is 4 light years away. And so I said on the outskirts of a globular cluster, they're going to be on average 1 light year away, and in the center just hundreds of AU, which is really just about the size of the solar system. So they're very, very close together. And while they aren't actively physically banging into one another, they are interacting a lot because of this density. And so there's a lot of star-star interactions, which can lead to some kind of cool effects, although I'm not really going to get into them. But for example, you can create binaries this way, and that can create things called blue stragglers. I love astronomy terms. And also not just for stars, but also for planets. So this kind of dense stellar environment would be very difficult for planetary systems to survive in because they would be disrupted by all of these stellar encounters. And in fact, we haven't really had a lot of success in searching for planetary systems in these globular clusters. Not to mention that planets tend to form more easily in more metal-rich systems, and these are population 2 stars. So one thing that's really cool about globular clusters is that this is a group of stars that basically formed at around the same time and out of the same material and have stayed together. So we can really examine them as a common population of stars. That is, they probably have similar compositions, similar ages, and so we can study them as a group and kind of learn a lot about those stars on their journey together as a cluster. So one particularly interesting application of this is to look at the HR diagram of a globular cluster. Now the HR diagram, I'm not going to get into the details of, but it's basically an empirical way of grouping together stars that we observe, where based on their brightness on one hand and on their color on the other hand. And there's this big section in the middle of the HR diagram that we call the main sequence. And this is where stars spend the majority of their lifetime. Our sun is a main sequence star. However, when stars run out of hydrogen to fuse in their core, they start to move off of the main sequence. And stars run out of hydrogen in their core faster if they are more massive. So we can actually look at a HR diagram of a globular cluster and see where it starts to turn off the main sequence, and that can actually give us an age of the system because we know the age of those stars that are starting to move off the main sequence. So here's an example from a very famous globular cluster called 47 Tucanae. I'm bad at pronouncing things. This is a very well-studied globular cluster that is the second brightest globular cluster in the Milky Way. And you can see here this kind of diagonal part that looks to be just like the regular main sequence, but up near the top, it started to turn off. And so we call this the turn-off point, and measuring that is what gives us the age. And then these other stars are post-main sequence stars, which we're not going to talk about, although I should probably do a video on stellar evolution at some point because it's pretty cool. So here's a picture of 47 Tuc itself, just because, like I said, cool pictures. Who doesn't like them? So globular clusters have been really well studied, not just in the Milky Way, but in other galaxies, and we know quite a lot about them, but we still actually have a lot of open questions about globular clusters, more than you might think. For example, we're not still entirely sure how they form, why they don't just dissipate like open clusters. Are most globular clusters formed in the galaxy in which they're now currently in, or are they kind of stolen from other galaxies? Like I said, most globular clusters that we know of are quite old, with these population 2 stars, and they're 10 billion years old. But there's starting to be evidence that there actually might be some younger globular clusters. And are those the same as these older globular clusters? Do they form differently? Why are there young and old globular clusters? What is the initial mass function of globular clusters? We know what the mass function looks like now, but what shaped it to look that way? Is that the way they looked when they were born? Probably not. So what is going on with them? What happens to the more massive or less massive globular clusters that might be different to medium mass, etc., etc. So yeah, they might just seem like a simple blob of stars, but globular clusters are actually really cool. Not only are they very cool looking, but they have ties into cosmology, stellar evolution, galaxy evolution and formation, even exoplanets. So it's just, they're really cool, and I hope you learned a little bit more about globular clusters. Thank you so much for watching. I hope you will come back for the letter H, and I will see you again soon. Bye.